Hi everybody, let's go through 12.2. We're talking about exponential functions. So our objectives would be to introduce the concept. Then we're going to look at graphs. We're not going to look at specific points today, but we're looking at the structure of the graph. Then we're going to talk about percent change and how we can adapt that to exponential functions. We're going to talk about compounding interest, then modeling other scenarios with exponential functions, and then finally we'll look at the specific natural exponential function. So first of all, this can be something that students get pretty apprehensive about because it's a concept that seems so new, but essentially you're just looking at the the type of function that will multiply a certain number. So if you look at the linear function you see here, you're just taking the number and you're increasing it by a certain amount or decreasing it by a certain amount each time. But that base number is where you start. So for this example, you start at 1 and you are, for this one function right here, you are increasing it by the amount of 1 each time. Then quadratics, you're taking each of those numbers, you're taking each of those numbers and you're raising them to a certain power each time, which is a square each time. Cubic, you're taking those numbers and you're raising them to the third power each time. But then, that works for the quartic and for the fifth power as well. So exponential functions, you're taking one number and you're raising it to a new power each time. And that's the big difference. It's not that you're doing something that is much more involved. It's just a different operation. Okay. So for example, you take 2 and you raise it to the first power, then the second power, then the third, then the fourth, then the fifth. It's just repeating that operation. And that works for each one of the numbers that you could have for your exponential base. So I actually have an image that I created I'd like to look at together. It's just restarting right now. Hang on a second. Okay, so you see this graph here. Hang on a sec. I'm so sorry. It moved from one screen to the next. Let me move that back, make it bigger so you can see it better. Okay, so you have this exponential function. I have it already graphed. It's y equals 2 to the x. And what you see here in this table is that I'm taking the number 2, and for each new x value, I am multiplying the number 2 that many times. That's what an exponential is. You're simply repeating the multiplication of the same number. In this case, because it's a base of 2, it's the 2 you're multiplying. It could be the base of any number, though, and you'll see that in a little bit. And you can just kind of see it plotting out this different curve. And that's why the curve looks the way that it does. It doesn't follow any of the patterns that we usually have. It's flat over here and just curves up very, very quickly because the numbers get huge the more you multiply. So you have, let me zoom back out so we can see the content. So now I've got here, oh, I'm so sorry, it zoomed out a little too far. So now I've got here the general formula or information for what an exponential function will look like. I will say to you guys that I don't know why, but this textbook uses C and A for their base and their initial amount, their coefficient. Every other textbook I see uses A and B. I don't know why they use these values or these letters. They still function the same way, of course, but if you move to another class and you see different letters, that's just because this textbook chose strange ones. But no matter what, you have an example here of something called exponential growth. It looks a lot like that one you saw just now where you're growing by a factor of 2 each time. But you can also have exponential decay, where instead of growing by a factor of 2, you could be decaying by certain factors as well. So if it's a growth function, then the value that you multiply is going to be bigger than 1. So like we saw, y equals 2 to the x. 2 is bigger than 1, so that was a growth function. If I want a decay function, it's going to be between 0 and 1. It's going to be a fractional value or a decimal value in there. So let's actually look at some examples where you're evaluating. You're given the function 10 times 4 to the x. That 10 does not get multiplied by the 4 because the 4 has that power of x. And they want you to evaluate when x equals 3. So you plug in the 3 for the x value that you have. Oops, I don't know why I took that one off first. So if you plug in the 3 for that x value, then you end up with, sorry, come on eraser. Sorry, my eraser wasn't moving. Then you end up with that 4 being cubed. So 4 times 4 times 4. I'm very zoomed in, that's why it looks like that, which is 16 times 4. I have to write much larger for this, which is 64. Okay, and then you can multiply that by the 10 because there's no longer an exponent there. Then that would get you the 640. Here we have, let me erase this first one just because it's kind of hard to see. 4 times 1/2 to the x. That number is between 0 and 1. This right here, this growth factor, or this factor, it's going to be a decay function because your factor that has the power is between 0 and 1. So I plug in the value that they give me for x. That's what you see here. And then I end up with, so what's happening there is I have 1/2 squared, so 1/2 times 1/2. Well, that's 1/4, and it needs to be multiplied by this 4. So, sorry, I have 1/4 multiplied by 4. That actually cancels out to 1. That's just one of the values that you would get in this decay function. Now, I blocked off part B so that way it doesn't confuse us or doesn't get in the way. So they say determine whether the function is a linear function or an exponential. And the solution is there, but I actually have a visual for how you can calculate this. So you have your table. I know they gave the table horizontally. I gave it vertically. If you want to determine what kind of function it is, you're going to need to determine how the function changes with each value. So our x values, it's just increasing by 1 each time. So you might say, oh, that's going to be a linear function. But then if you look at your y values from 64 to 16 and 16 to 4, if I were to try doing my change, let's see, 64 to 16, what is that? That's not 32, that's 40, not 8. Was it 48? No, 40. I'm just going to write it down rather than try and calculate it in my head. 64 minus 16, that gives me a 5. 14 minus 6. Oh, it was 48. I don't know why I second guessed myself there. So that's subtracting by 48. Okay, so then I go to make my next change. If it's linear, I expect that to be the same again because this change was the same. So if it's linear, that change will be the same. But when I go and I subtract it, 16 minus 4, that's minus 12. 16 minus 12 gets me that. Those are different values here, while these are the same values. So this is not linear. Okay, it can't be linear because those values have changed. And if it's not linear, then it's something else, of course. In this case, we know then that means that it's exponential, but still. So you look at it and you can say, oh, it's possible that it's changing by a pattern of a different kind of pattern. So you can get rid of this. Let's take a look. If I looked at this and I said, what is it multiplying or dividing by? and I get the same number each time. 64 divided by 16 is 4. I'm sorry, 64 divided by 4 is 16. 16 divided by 4 is 4. And 4 divided by 4 is 1. So because it's actually dividing by a certain amount each time, the same amount each time, then that means that this is an exponential. So for linear, when you try and find that change in x and y, the change in y, the change in x, then that should be an equal fraction each time. The slope that we talked about before. I'm not going to write it down, but quadratics, if you were to do this, it's actually going to be an equal fraction if you do the change twice. I'm not going to write that down. But exponential, when you do that change in y and that change in x, when you do that calculation, it's going to be, so the change will be by multiplying or dividing by a specific number, the same number each time. I'll write that down instead, same number each time. That's a very easy way to tell if it is an exponential function without being able to look at the graph. I'll zoom out so you guys can see that, and then I'll show you what answers they gave. So they said each time x increases by 1 unit, f of x decreases by a factor of, oh, I couldn't have it covered, sorry, of 1/4. So this is an exponential function with a decay factor because you're dividing, okay? Let me write that down too. Decay, you're dividing. And growth, you're multiplying. So it's a decay factor. In this case, hopefully you guys recognize if you're dividing by 4, that would be a 1/4 decay factor. Okay. And then, so they took that 1/4 and they wrote it down. And also notice that they have this 64 here. Let me zoom in. 64 showed up in that table at 0,64. That value, that C, you can find that number usually, I'm not going to say this is every time, but you can usually find that C from the y-intercept. The only reason that you wouldn't be able to find that is if the graph transforms, if it translates around with that h and k that we talked about, but we're not going to do that in here, don't worry. Okay, I'm sorry, let me leave that there for people to pause if they need to get that down, and I can move on to the next one. Okay, then part B, problem B, they want you to do the same thing with this new table here. So you look at the new table, I've got that written down right here on the side. Let's take away that. So it's changing by 1 each time. And this one, it's changing by the same amount each time. So that means that, I'll write that. We'll look at that in a second. If it's changing by the same amount each time, then it's linear, okay? And you can use your practice that we've done before to find the slope. Change in y over change in x. You plug in your values and you get 2. And your y-intercept, or your b, is the y-intercept when x equals 0. I think I might have deleted that 0 when I deleted that. Yeah, when I deleted the x, or the big block. So the coordinate 0, 3, that's when x is 0, so your y-intercept, b, equals 3, which is what they have written here. Slope of 2, y-intercept of 3. So then you can write that in the form y equals 2x plus 3. Give people a second to get that down, or to pause it and process and rewind if you have to. We'll move on to percent change. So this might seem like it doesn't fit the rest of this stuff, but percent change will affect the way we can apply exponential functions. So they give you the formula here. They say when something changes to a new amount, you can calculate the percent change with this formula right here. So you take the values and you can subtract them and then divide them, and then multiply it by 100. Now, this kind of doesn't really fit scenarios to me. So the way that I have always taught this to students is I say it's the final value minus the initial value, final minus the initial, all divided by the initial. So you'll get this fraction or this decimal, and then you can multiply it by 100 to turn it into the change, or to turn it into percent. Turns the change into percent. Change. So I write my formula out, final minus initial divided by the initial. They're still going to do the a minus b, or b minus a all over a. I don't like that because it just seems arbitrary to say a and b. I highly recommend writing your formula down like this. Students have always told me that it is easier to relate to the problems like that. Okay, so I actually took this one slide and I copied it twice because it has A and B on it, and I thought this way you could see the A work and then see the B work later. So it says find the percent change if an account increases from 100% or $100 to $300. If it's increasing, you should expect a positive percent change. So positive percent change. So let me see. So it says let A equals $100. Well, that's my initial amount. And B equal $300. That's my final amount. I still have their formula written down. I didn't write down my work with the formula, but you can see that you'd say the final value, final, minus initial, all divided by the initial, multiplied by 100, will get you, 200 divided by 100, all times 100. So it's a 200% increase because it's a positive value. That's how A works. Let's look at B. Find the percent change if an account decreases, and they wrote this kind of funny, decreases from 100 to 300. I think they meant decreases to 100 from 300, but they just had a little bit of a mistake. They did say decrease, and you'll see it in the work in just a second. So I do have that block right there in right below it. That's the A work. Okay, so let A equal $300. That's our initial value. And B equal $100. That's our final value. Erase the arrow on accident. So we want to plug these values into the percent change formula. 100 minus 300 divided by 300. That matches final minus initial divided by initial. Do your calculations. That's negative 200 divided by 300 times 100 to make it a percent. And when you do that final calculation, you get negative 66 2/3% drop or decrease. Okay? Now here we can start relating this percent change stuff to exponentials. So it says an account that contains $900 decreases in value by 30%. So it's going to be a decay function because it decreases. Find the decrease in value of the account. So let's find the actual amount that it changed to. It's a lot like finding the discounted price at a store. Then find the final value of the account. By what factor did by A did the account decrease? So let's look at A first. Find the decrease in value. Oops, sorry, that's not an eraser. So you take the value and it's decreasing by 30%. So they say, okay, well, what is this number 900 multiplied by 30%. And they have the negative because it's decreasing, so it's going to drop $270. So say, well, what is 900 minus $270? $630. So that's the new price, or I'm sorry, the new account value, because it decreased by that much. So you have your final amount. This is our final. This is our initial. It says, by what factor did the account decrease? I'm so sorry. So they're not asking about percent change exactly. They're saying by what factor did it decrease? So if you count that initial amount as 100% of the price, so 900 was like 100%, and 630 is 30% less. You say, okay, well, how much percent did I drop? I'm sorry, what percentage was left of that 900? So it was 100% minus 30%. Your account has 70% of what it used to, or that's the factor, okay? So that's why and I have it written as 70%, but they actually rewrite it just as 0.7. It's the same thing, doesn't change it. They've got this formula written out for percent change written in exponential functions. Please note that the growth factor that they give you, A equals 1 or 100% plus the rate, is written out as the same as the decay factor. That's because growth and decay, they both sit in the same position in the function. They're both at the base of the exponential. So the growth or decay factor, that's the base of the exponential. That's what gets multiplied out, like we saw in those that GIF earlier. Okay, now, but they do tell you that growth is when that base is greater than 1, and decay is when that base is between 0 and 1, which we talked about before. Let's see. One thing, they use the letter R, percent. They don't really say that they're saying R to represent the rate that it changed. Okay. So you've got this word problem here. You got a lab that a lab culture, meaning like a little sample that has 100,000 bacteria per milliliter, and it's decreasing. Okay, so I'm just going to write decay. Like maybe the bacteria are dying off, I guess, by 10% each hour. Okay, so first we need to write the formula for the exponential that represents this scenario. Well, they give us a bunch of information, and we can pull out all the pieces. So our initial amount, which is what they call C, is 100,000. Our rate, what they call R, is 10%. Okay, but it's decreasing. Okay, so you want to think about if it decreased 10% in 1 hour. So in 1 hour, what percentage is still left? You say, well, you had 100% and you subtracted 10%, so it's 90% left. So your rate, you can't put the percent symbol in a formula, so you have to write it as a decimal. So your rate is 0.9, okay? So we have, I'm so sorry, the rate, they use the letter A, remember, for that growth factor or the decay factor. So decay factor equals 0.9. Let me move that over a little bit, sorry. I tried to have this so that way we didn't have to do a lot of editing. And so you have all the things you need to plug into the general formula that they gave us here. A equals CA to the x, which we can write down. A of x equals CA to the x, or you can have it as so let me erase that part, sorry. A of x equals C times 1 plus R to the T. Okay, in this case, we're talking about time, so we can use that if we wanted. So you would say A of x equals 100,000 times 1 minus 0.1, which we've already done that calculation. Hang on a second. Oh, I'm so sorry. I did say A to the x. I should say A to the T. And equals 100,000. Just a second. Let me pause my video real quick. Okay. So sorry. I paused the video for a second to do something. Equals times 0.9 to the T, which we already said that our decay factor is 0.9. So you could have written that here too. A to the x equals 100,000 times 0.9 to the x. And I'm using x. You can rewrite it as t, again, because we're talking about time. You can change that variable. That's fine. And that is what you see here as well. Just adjust to whatever variable they give you. I like to use t whenever we're working with time. I go back and forth. Okay, that was part A. Then part B says evaluate B of 3 and interpret your result. So they plugged in 3 to the function. So you can see the 3 there as the exponent. And just simplified it. You're going to need a calculator for that. You can't do that by hand. And they got their value, and it says to interpret it. That means to think about how it works in the context of the problem. So 72,900, that's bacteria per milliliter, just like they told us up here, bacteria per milliliter. That's what that is. And it's, I don't know why they do the semicolon, sorry, and that's after 3 hours because you plugged in T equals 3. Okay. That's how you can, that's as simple as you need to go for interpreting this stuff. Now, I broke down the way that you would plug this all in very thoroughly. Let's look at another one similar. Sorry. So this first part here, they're telling you the general formula for when we talk about compound interest. These formulas are all going to be very similar to each other. The only reason that they're ever different is because you might have different values that you need to adapt to the general idea. Okay, so P dollars, that's your total, or I'm sorry, that's your starting amount, because that's what's deposited in an account. And there's interest that's paid from the account holders or the account creators. This is like a bank, okay, with a certain interest rate. So let's say you get back 5% every year that you have money in the account. For anyone who doesn't know why, it's because when you put money in a bank, the bank can use the money that they hold for you for other business on the guarantee that when you come back, they'll have it there ready for you. So then T years, that's your other value. So they have it all put together in this one formula. Notice it's almost exactly the same as the formula you saw here, just different letters. One thing to note, it is years. So I do have that written out over here as well. Let me see. So A is the final amount, P is the starting amount, R is the rate, and T is the time in years. So if you get a problem like this and you're supposed to calculate in months, you're going to have to make that a fraction of years. Or even in weeks, you still make that a fraction of years. Okay. Notice that they say that the growth factor is 1 plus R. That's the same as what we've talked about as the growth factor and the decay factor. It doesn't change. We keep using that as the way we break this down. It's 100% plus whatever change it it has from there. So here's an actual example. I'm sorry, let me let you pause this if you need to and move on. Here's an example of retirement account growth. So this 18-year-old put in one amount at the very beginning, okay, and doesn't change it at all, doesn't add to it at all, which is not great, but this is just for this one example. And this 18-year-old worker has an excellent account for him, 12% interest at the end of each year, okay? So the years is the only thing that we need to worry about. It's not like it's growing every month or anything like that. So they want to know how much money will be in the account when the worker is 60 years old. So the first thing we need to figure out is how many years is this going? So 60 years started out, he's 60 years old at the end of the account, started out at 18, so it's been in there for 42 years. That's why you have the 42 in their calculation. And that means that your starting amount was 1,200 with a rate of 0.12, because you can't write it as a percent, for 42 years. When you plug all those values in, and that's all that this is doing is plugging the values in, you get this amount. Notice they even show you what it looks like on a calculator, because I want you to see that. So this 18-year-old from, and I mean, I don't know of any accounts that have rates like this. This just doesn't exist. But let's pretend that you do stumble into a job where you can do that. All he did was put in money one time and made such a huge amount of growth over those years. It is very valuable to try and compound your money like that. Okay, here's another example. This is an account that's annual interest. Again, I don't know where we're seeing 6% growth. This is the starting amount, but this one, notice it says it's compounded daily. So this one's going to be a little bit different. You have to think about how that affects your time. T in years, you're going to have to change that value there. So notice that they have this new thing. They have this N to adapt that. So you have to adjust the way that you calculate that time that you plug in up here. In this example, you plugged in the 42 and it was no big deal because it was just one time per year. But I mentioned that it changes if you have to do it multiple times a year. So they multiply the number of years by the number of days, because of a number of times in each year. But that does change the interest rate calculation. You have to take the rate and divide it by the number of times that you've seen, that you broke it down. So they don't actually give you a formula for this here. I'm going to write the formula down because it can get very difficult to keep track of all of it. This is to help whenever you're compounding more than once in a year. That's what this formula would be for. So you take the initial amount, you're still adding to the 100%, but you take your rate and you divide it by the number of times in a year. Let me fix this parentheses real fast, sorry. And then when you go to your power, you do the same thing. You have to adjust that too. So you have your number of years times the number of times per year. Textbooks like to give this as a separate formula usually. I can see why they didn't. It's just more work. So first thing they did for this one is they simplified each of these values. So this value here and this value here, they simplified those. Sorry. But it still works out to just be a calculation that you just plug in. So in 5 years, you've increased by this amount without including any new money. When you add in new money, the calculation gets more intense. All right, so here is an example that is not related to money. So this is just modeling a scenario. So you have this intersection, you have these vehicles that come through, and they give you the function to model how the probability that there are no vehicles at a certain time or within a certain amount of time. Okay, now this is in seconds, and it says randomly each hour. But we're talking about this function in terms of seconds. First thing we want to do is we want to compute what it looks like when you have the value 6 or 6 seconds. So first, let's plug in 6, and you get 0.55 for your probability. So about in 6 seconds, there's about a half a chance that it could happen. And they show you the graph, and it says to discuss the graph. And so you don't have to get really technical here. They say the graph decreases so that as time passes, there's less chance that a car is not going to come around. So the longer the time there is that this road is left alone, the less chance, or left there, the less chance that it won't have a car pop in. And it says, is an example of growth or decay. We should be able to see just by looking at it, honestly, because the graph goes down as time goes along. It's a decay function. So the graph is decreasing, like I said, goes down. And once you look at the number in the function, that number, yes, it's almost 1, but it's still less than 1, so this is actually a decay function. So this modeling that you look at here, this is not calculation heavy, it's interpretation heavy. You have to think about what's logical for the scenario. Okay, so that was modeling one thing there. They do mention specifically the natural exponential function. I don't want you guys to worry about this. I don't want you to look at this and say, oh, I don't know how to do this. This is scary. It's not. That is just another exponential with just another number. It does continue on forever, and they only gave you part of it here, but it's just a number, okay? So it works almost exactly like everything else, just with its own values. So if you take a look at this one here, I have that original graph showing. I couldn't put this in OneNote. It wouldn't pop up. But anyway, I've got this original graph showing here where the black line is y equals 2 to the x. So I flashed, oh, I'm so sorry. My finger touched the screen. So I flashed each of the lines to show you that. And then I show you that you build the e to the x function the exact same way. So you plug in 1 for 0 because there's no e's there, and then 1e, then 2 e's being multiplied, then 3 e's being multiplied, then 4 e's being multiplied, and so on and so forth. And that's how you create it, just like how you created 2 to the x. So don't think that it changes just because it's an e instead of a number that you recognize. E is not even, it's not even 3. It's 2.7 something. 718, I think. Let me see. Yeah, 2.718. So here's an example where E pops up in a calculation. So population of Texas was this amount, 26.5 million, and it was growing. And it's growing, first of all. That means it's a growth function. And they give you the rate. They tell you the population at 2013, and they say after 2013, this function here can model that population growth. Okay, so this says estimate the population in 2017. Okay, 2017 is 4 years after 2013, so you plug in 4. So you see they plugged in a 4 here. And you do the calculations. they put an approximately there because they just want to round it off because you're talking about millions, so you don't need to go all the way down to the ones place, I guess, is their thought thinking. I like to just put the number, but you're still just estimating, so it's okay. They'll tell you what's a valid estimation point. So this population would be about this amount, about 28.5 million. That's just another way to approach or to that you could be